feedback control systems, you put in the command, and instead of doing what you told it to do, it does this integral of what you told it to do, and therefore it's always making some error. And if it's a feedback control system in a factory that's doing the same operation 500 times a day, it's doing the same wrong thing 500 times a day. And then you can say, that's kind of stupid. Can't I learn, do some learning from what I did, what happened last time, try to improve the performance next time. So iterative learning control, has some sort of command you want a robot to do, let's say, and you measure what it did when you gave the command, and that goes in here, and this is what the system actually did. Then we're going to change the command to be something. We want to change the command by looking at the error in each time we run the command, we look at the error and change what we ask for, trying to get 0 error. So now in an equation like this, you can say, maybe I shouldn't try to iterate. If I've got a mathematical model, and I know that I'm going to get the wrong answer when I put in y star. Maybe I can go up here, and I put in y star here and here, and I'll solve for the command here, which is no longer the desired output. It's something else, something different. But I'll solve for the output that produces the solution y star. Okay, so that's that. So if I could find, let's call I'll replace y star. I'll replace it by some u, and then I say dy star dt equal, well, let me put a plus k times y star, divide by k, and that equals a u. So I just did a so-called inverse problem. I plug the solution I want into the model, and I solve for the input that would produce the solution I want. Okay, so that's an inverse problem, and if I have a model, you might say I should be done. Now, I'm only done in the sense that, well, there's two things that are wrong with, are bad about it, but one form of adaptive control, so-called, uses this sort of thinking and says, maybe I don't know the real world model, but I will watch the data, and every time step I will make a model. I'll use the data to make improve my model. After I have a model, I will use it in this way to find the input that produces the output I want in the next time step. So that's called indirect adaptive control, and it's indirect because it makes a mathematical model from the data and then inverts the model to find the input to produce the output you want. So it's got an identification step coupled with a control step, and in this case it's what people would, if it's a difference equation, you'd call it one step ahead control. You're asking for 0 error in the next time step, based on your model and your measurements of where you are at the current time step. Okay, so now iterative learning control is analogous to direct adaptive control, where we ask to find the input without going through an identification step. We want to make some convergent process that will converge to this U that produces the response we want, but we want to do it based on measurements in the real world instead of our model. Now, let me comment about how effective the methods can be. There was a robot at NASA Langley Research Center. A guy named Jianan Zhuang brought in this robot, and we did a bunch of experiments. And if we made a model of the robot and inverted it this way, then we could improve the tracking of a high-speed trajectory by a factor of about 50. So we make a model. So we ask the robot, every link of the robot, to move 0 up to 90 degrees and back down to 0, and it's 7 degree of freedom robot, so all joints are moving at the same time, 90 degrees and back. And the feedback controllers get a maximum error of about 9 degrees, all of them. Then you say, I'll make a mathematical model and I will solve for the command. Instead of asking the trajectory from 0 up to 90 and back to 0, I ask for something different, but it's whatever my model says would produce the 0 up to 90 and back to 0. So I'm giving a command to a control system which is not what I want the system to do, but it's supposed to have the property that my system does what I want it to do when I tell it to do something different. Okay, so that's a factor of 50 improvement based on making a mathematical model. We could use OKID and make our mathematical model and then solve for this. Now, I can take a learning control law which looks at the error every run and adjusts the command and try again, and I apply it starting just from the feedback control system. In approximately 4 iterations or 3 iterations, I'm at the factor of 50 improvement that I got by inverting the model. When I continue and iterate for 12 times for learning, I get a improvement by a factor of 1,000. So the maximum error for the robot following the trajectory started out at 9 degrees maximum, and after 12 iterations of just adjusting the command, looking at the data for a run, adjust the command, do it 12 times, we get high precision motion by a factor, improved by a factor of 1,000. Instead of 9 degrees, it's 9 divided by 1,000 is the maximum error in degrees. So this kind of learning process is a way of getting more precise motion than you could ever get from any mathematical model you chose to produce. We have to keep that learning law running to go from day, well, let's try to make perspective of how much improvement that represents and how much possible improvement there is. If you ask a robot to do a specific trajectory and just ask it to do it many times, we can take data about how different the trajectory was, how different the measurements were each time. And there's always some noise, some non-reproducible things that happen, so it's never really the same each time. And you can't use a learning law that in order to get down to that error level, because you look at what happened last time, assuming that it will happen again, and you react to what that error was. If it does not happen again, then you're reacting to something that is not going to help you. So that's the absolute limit of how much you could learn. In this case, this is maybe a factor of 4 or 5 above that reproducibility level when we get done improving the tracking by a factor of 1,000. However, that's a measurement of reproducibility on any particular day. You just take a bunch of measurements. If I come back and measure it again tomorrow and the next day, then this is much better than from one day to another. And that means that we're fixing errors of how different the robot is tomorrow than it is today. And nobody knows why it's different tomorrow. Maybe the sun's shining in the window. Maybe the fans are on and they weren't on yesterday. Or maybe something is different, and we fix errors in the way the robot moves, of the size of how different it is from one day to the next. So the methods can produce very high precision motion. So now, how do we do the learning? The simplest concept is, if the robot link, let's just look at one link and say, I've asked it to move this way, and at a certain time step, the link was 2 degrees lower than I wanted. The simplest thing the type of learning control says, well, maybe I should add 2 degrees to my command. If I can just do that over and over again for every time step, will it converge? Well, mathematically, we can prove it will converge. And it's actually a fantastic mathematical proof, because it works for a very large number of systems. Any linear time invariant system, it works. It works for linear time varying systems as long as the time variation is the same from each run. It works for nonlinear systems as long as it satisfies a Lipschitz condition, et cetera, et cetera.